Anyhow, so this is CS 746. It is Wednesday, February 12th. Today's topic is exploratory data analysis. I thank those of you that are in the room for braving the weather to come out and be here. Personally, having grown up in the North Country in Wisconsin, South Dakota, I think this is glorious weather. I'm enjoying the heck out of it. The rest of you may have different opinions. Anyhow, so before we dive into the lecture, I'm going to take a quick detour to Blackboard. Pull this on over here. So we promised that we were going to have the folder with the data files in it up yesterday. We didn't get that done just yet. Hopefully we'll have it up today. Anyhow, it'll be done before the weekend. We'll get that posted for everybody to see. So under the lecture slides, just want to point out that the statistics lectures and hypothesis testing are all listed together in one big clump in there. So we didn't have a separate lecture for the 5th and 6th, which was the statistics for data science, and then the hypothesis testing stuff was on Monday and Tuesday. That's all in together. We did upload statistical tables, a PDF file, and we have the two different lectures and explanation about where we're at on the project up there for you to review on the recordings there. So if you missed those, I think Harika did not go through the project slides on Tuesday, so we'll remind people on Thursday that that's available for them. Anyhow, there's also a homework out there. One person sent me an email saying, where'd this homework come from? And so I'm going to tell you that I put it up there. It's my fault. Anyhow, big homework one is on data cleaning. If you look at the homework, as I say in here, download these files, follow the instructions in the data cleaning .ipython notebook file. If you downloaded that right away on Monday, you got instructions that had a couple extra steps. 4 and 5. I've deleted those in the newer version. It doesn't. That's the only thing that's changed. Anyhow, so if that's confusing, you can just do steps. Recognize the steps 1, 2, or 3 is in the program that's uploaded. Those are what the code currently does, and then the steps that I want you to do are further down. So, okay. Any questions about where we're at on that big homework? Okay. And then, of course, when we get in today's lecture, during this, we'll talk about this file, which is the IRIS exploratory data analysis code, where we're actually taking the IRIS data set and doing EDA on it. And we're going further than the homework that was assigned. And basically, I wanted to have a data cleaning homework, so I stripped out some of the EDA stuff and shared that as only the data cleaning. We're going to do EDA too in this class, but we're going to hopefully try to get that done under the guise of the project. That's enough of the background. So we're going to continue on our course today, and what we are doing today is discussing exploratory data analysis. Part of explanatory data analysis is data visualizations. And so you see I've highlighted just a little bit of the data visualization. We're not going deeply into data visualization today. There are just tons of tools out there for doing all kinds of visualizations of your data. We're going to try to do a lab on Microsoft's Power BI, because that's a piece of software that's free to everybody that's a student at Wichita State, already paid for. They have a contract with Microsoft. So the only time is we're going to figure out when we're going to do that. So what is EDA? Why is it important? What are the steps, and how do we perform one? And we're going to perform an EDA on the IRIS data set, and you'll see that basically data cleaning kind of fades into exploratory data analysis. Exploratory data analysis is you've cleaned out the obvious errors. Now you're trying to find out if there's anything that first of all, what the data is telling you, and second of all, if there's any more mistakes or errors in the data, right? So exploratory data analysis is used to take insights from the data. We use that to find patterns, relations, anomalies in the data, looking for weird stuff in there. We're also looking for errors still, because we don't necessarily capture all the errors up front. We're using statistical graphs, other visualization techniques. We're trying to get the maximum insights from our data set. We want to uncover the underlying structure in that data. We want to find out what the important variables are in the data set. And we want to try, hopefully, so that we can ignore the unimportant variables, right? So, because the more stuff we have to look at, the bigger our analysis task is, right? So then we want to detect outliers and anomalies, if there are any. We want to test our underlying assumptions. We think we know what this data is. Are we correct? We want to determine the optimal factor settings for when we're running our models. You know, if we're going to do a linear regression, we want to determine the correct variables to use in our linear regression. If we're doing principal component analysis, we want to determine what our proper scaling features are, factors are, things like that. Of course, the main purpose is to detect errors, mostly outliers and patterns in the data. We want to understand the data before making any assumptions. If we are misunderstanding what our data is, we'll make bad decisions about what we can do with it. We'll do things that it can't do. We'll fail to extract useful information out of it. So we want to ensure that the results we produce are both valid and applicable to whatever the business is asking you to do. You know, your boss is going to ask you, do an analysis on this data set, right? And you're going to say, you know, I'll do my best to do a good analysis, right? And then, of course, if your boss, your stakeholder, your customers are asking you to do an analysis, they might not know quite what they're looking for. They might not have a great understanding of statistics. You can take your information you glean from exploratory data analysis, put it in a nice graphical format, turn it around, present it back to the person, say, is this the kind of stuff you're looking for? Is this what you understand the data is doing? So make sure that the stakeholders, again, that's bosses, companies, customers, shareholders, things like that, make sure they're asking the right questions. The EDA can answer questions about standard deviations, categorical variables, confidence intervals, things like that. So what are the steps? 5 steps. 1, provide descriptions of your sample and your features. 2, check for missing data. 3, look at the shape of your data. 4, identify significant correlations. And 5, spot and deal with outliers in the data set. So how do we perform it? Well, we're going to start with the IRIS data set. So we're going to go through some of these slides, and then we're going to go back to the code and actually run the software and watch it work. So this was, of course, the IRIS data set is basically, if you've studied computer programming languages, you most of them start with a simple program where you type in hello world, right? So the IRIS data set is the hello world program for data science. If you don't get that joke, that's okay. It was collected by Ronald Fisher and Edgar Anderson back in 1936. They went to some field in Lake in New Brunswick, Canada, and they went out there and started measuring a bunch of flowers, which is kind of a comical thing to picture. You know, guys down hands and knees measuring flowers. I don't know. Anyhow, they had 5 things they looked at: the petal length, the petal width, the sepal length, the sepal width, and the species type. What do these mean? Well, irises have some, what we say, look like flowers or petals that are going up and petals that are going down. Well, the petals that go down, the ones that the bees land on when they're going to go get the nectar, those are called sepals. And so the iris tends to have small petals going up and larger sepals going down. So we can look at the sepal width and length. We're seeing 5.1 centimeters, 3.5 centimeters, 7 centimeters, 3.2 centimeters, so on and so forth, where the petals are 1.4, 0.2, so on and so forth. Petals are generally narrow. Some of them can be quite long. 6 centimeter petal, right? So long, skinny things. Anyhow, so we're going to start by doing step 1 and step 2. We're going to provide descriptions of our sample and our features. We're going to check for missing values. So we start with a df.shape. It says we got 6 columns and 150 rows, or 6 features and 150 observations, or 150 samples, of which we measured 6 things at each sample. What are the types of the data? Well, we have our nice clean iris data, which I assume you've all downloaded the homework by now and run it against the clean iris data set. You will see this information. There's an ID column, which is a 64-bit integer. There's a sepal length, petal width. Those are all float 64 floating point numbers. And then finally, there's a species, which is a string, which pandas will call that an object. And there are no nans listed on here. There are no, surprises. We don't see petal length being an object, right? So on and so forth, right? We do a df.describe. df.describe goes for every column. It gives us the distribution. So we're going to assume, we could test whether the distribution looks like a normal distribution or not, right? Normal distribution is symmetric. Are we seeing that in our mean, our min, our minimum and our maximum? Are we seeing that in our 25th and 50th percentile? Well, let's look at the ID here. There's 150 IDs. The mean is 75. The standard deviation is 43. Minimum is 1. The maximum is 150. This is starting to look a little suspicious. The mean is 75. 25th percentile is 38.25. Of course, these are just the numbers 1 through 150. Right? This is not useful data. Right? But Pandas doesn't know that, so it's going to give you statistics on everything, right? Sepal length and sepal width, a little bit more useful here. We can see the mean is 5.84 centimeters. We can see the minimum distance is 4.3 centimeters, the maximum 7.9. So we kind of get a feel for what the distribution of the data looks like, right? We can look for the is null. Are there any null columns in there? We can look for duplicates. We can check for duplicates in the data, whether they're expected or unexpected. So for instance, we want to look at what the species are. If we just dump the species column, we'll see 50 of each species. So we say, go ahead, just drop the duplicate so I can only see the individual, just one entry for each species, right? Or I can just do df.species.unique. It'll give me an array with the 3 unique values that are in there, right? So I can see I've only got 3 species in there. And there are more species of iris. Maybe there's an iris data set floating out there with, completely different species. Who knows? All 3 species have the same number. So now we ask ourselves, is our data set balanced? If we had 50 samples of Setosa, 50 samples of versicolor, and 2 samples of virginica, we would not have enough information to say anything about the virginica species, right? Or anything particularly useful about it. So we want to see that our data set is relatively balanced. It doesn't have to be precisely the same thing. If we have 51 and 48 and 52, something like that, that's balanced, pretty close to balanced. And again, when we get into further lectures, and if you study statistics, of course, you know that imbalanced data sets can cause you serious problems with false positives, false negatives. Visualizing the shape of your data. So we're going to use Seaborn and or matplotlib for our plotting libraries. These are the 2 main libraries. Seaborn kind of lives on, is a improvement. It's got all the stuff in matplotlib, a few things more. The syntax is a little bit different. Some people find it cleaner. Other people think that matplotlib is just the perfect tool you need. You'd never need to use Seaborn. And there are other things. This is the cool thing about open source software, is if you don't like the tool you're using, there's always another one out there. The only problem is sorting through the huge number of different possibilities that you have to deal with, right? So there should be like a class in determining what is good open source and what's not. Yeah, maybe that's in the cybersecurity, because the bad open source has got 1 cybersecurity holes in it, right? Anyhow, so this confirms, in any case, we do a count plot, gives us a bar chart of how many we have in each one. Of course, clearly it's 50, 50, 50. We want to visualize the relationships between the variables. So we can start doing scatter plots. We say we want to scatter plot with this. The X column, we plot the sepal length. On the Y column, we plot the sepal width. We tell it to color the data points based on the species column. And it'll assign automatic colors for us. And we, of course, tell it what data you use, right? We place the legend on there. We can tell it to put the legend outside the figure. And we can show the plot. When you're doing plotting using Seaborn or matplotlib, of course, you're doing all these calls to set things up. And then you call plot.show. Or I think it's plot.plot in matplotlib. Memory memory fails a little bit there. Anyhow, but here we got setosa. We're plotting sepal length on the X column, sepal width on the Y column, on the Y axis. And of course, we can see clearly that there is obvious separation between setosa and the versicolor and virginica. But in terms of sepal length, in which virginica and versicolor have a lot of significant overlap in there. So if we're going to try to use this characteristic to determine what species, someone brings in a flower into the lab and says, what kind of iris is this? We get out a little measuring stick and we measure the petals and the sepals, and sepal length and width are not going to tell us, much about differentiating between versicolor and virginica. Right? We can compare the petal length and the petal width. And there we go. In this case, we see some actual, even more differentiation between setosa. And we see that there's actually some reasonable differentiation between versicolor and virginica. There's a little bit of overlap, right? Not huge amounts. We can do what's called strip plots. If we want to look at a single feature and ask what the variance or the variability is of that feature. So we can say, give me a strip plot of the sepal length with the X column or the X axis being the species. So the category is used. So it's just going to label it setosa, versicolor, and virginica. And then it's going to give us a strip plot where it actually kind of, the number of points on the line or on each row tells us how many observations there are in that bucket. It's kind of a sideways bar chart, maybe. Sideways histogram. Another way to look at it is the violin plot, which actually contains hidden within it a box plot. And the violin plot has the little white dot in the middle, shows where the median is. The little kind of box in the middle shows us the 25th and 75th percentiles. Here's our whiskers. And then this is actually kind of a shape of the relative number of observations at each finely graded bucket in our data set. So, and it's called a violin because, if you get one of these with the right data outlook or data layout, it looks just like a violin. So, yeah. We can do pair plots. We can do a pair plot of all the variables at once instead of doing scatter plot for A and B and B and C and C and D and A and D and so on and so forth. We can just say do a pair plot, right? You need to do this one and not this one. Why? Well, you can do this. You can just do pair plot on your data. You say go for it. The problem is you're going to have an extra row, an extra column, and that row and column is going to contain the ID field. And you're going to look at that and go, wow, this is a great predictor of the species because that data file is sorted, right? So the lowest numbers, yeah. So you want to be careful to take the non-useful columns and drop them at some point. We can leave them in the data set and just do a drop of ID on the first axis, and then we plot it, or we can just go ahead and leave it in there, or we could in fact say df equals df.drop ID and throw it away altogether before we get to this point in our analysis. Here's what our pair plots look like. We'll bring those up on the screen in a little bit. We can do histograms, individual histograms. Here's some examples. And we're using what's called hist plot on here, or hist, yeah, okay. Whatever. So the sepal length, what we can see with our histogram plot is the tallest bar tells us the number of observations in that bucket. So, about between 5.5 and 6 centimeters, we have 34 observations. Between 7 and 7.5, we have someplace about 9 observations, right? So on and so forth. So each of these is just telling us where it is. Sepal length, the highest frequency is about 70. And petal length, what's the highest frequency? Precisely 50. Remember, we looked at that one scatter plot and we saw that the iris setosa was off all by itself. So you can see every single setosa observation is very, get that out of the way, there, is between 1 and 2 centimeters. On the petal width, it's similarly Almost every single one of those is under half of a centimeter, right? At a width, yes. So we can do histogram plots, which help show us overlaps with the species shown in there. And there are many options on this to whether to add KDE, kernel density, E. Exploratory. E stands for exploratory. Yeah. No, kernel density effect. No, that's not right. Whatever. Stands for kernel density function, anyhow. So what we're showing is whether we draw that smooth line on our to represent our bar chart as a uniform distribution. And there we got our different ones. And finally, we can do 3D visualization. Let's go back now to our code. Here we go. So this is the IRIS database. We're going to run it. There are actually two ways to load the IRIS database. We can load it out of sklearn. If you import sklearn, right, your data sets, there's a whole bunch of data sets in the sklearn library. And one of the data sets is the IRIS data set, and plenty of other ones. These people at sklearn are very careful to make sure that these are clean, well-curated data sets. They actually had one data set we started using when I first started teaching this class that they had discovered had ethical problems with how it was collected. And so they took that data set out of there because, you know, it's like, you know, Nazis doing medical experimentation on people. Do you really want to try to use that data, you know, for yourself? No, you don't want to, you know, unless, you know, there's questions like that arise. So as they do things like that, they're careful to use, you know, clean data sets that weren't misleading, as it were, because that was the violations in that data set were like causing you to get wrong answers. So we can load the IRIS data set directly out of that. We print the description, and here's the big old description of the data set. And we can then look at the head of the data set. And so here we see that there are 1, 2, 3, 4, 5, well, actually only 4 columns in here, because this is actually the line number that was added by the sklearn the pandas data set when we loaded it into a data frame. Or we can load the iris.csv file. And of course, this is what we're going to do in our homework, is we're going to load iris.csv. If we were to look at the shape here, on this data file, run this line, and I do a df.shape, and run that. Run. We have a df.head. Oh, not a method. Sorry. It's just attribute. df.shape is 150,4. When we load it in from the comma separated values file, of course, we get 150,6 because there's an ID coded in the CSV file and the species is coded in the CSV file. In the data set, they've actually separated out the species because that's what we're looking for. That's the target that we're going to be trying to predict based on the other things. So they've already tried to pre-process the data a little bit if you load it from sklearn. So we're going to use the comma separated values file, 150,6. We look at our info. We can see that everything's clean. We look at our description. We've done that already in the slides. We look at our null values. We see if there's any, you know, missing values. If you load the IRIS errors data set, you run this command, you'll see that there are some lines that have missing data, right? We have duplicate, and again, this is just see what the species are when we have lots of duplicated information. Or we can just say, show me the unique species, and then I get the object out of there that tells me what the species are. We can look at this balanced. We've been through all this, checking for the missing data, dropping the duplicates to show that there are no duplicates left. So if there are errors in there, this is how we fix it, right? We have not availables. We can say drop not available numbers where there's missing entries, and we can drop duplicates. This literally will clean everything up without you doing any thinking about it. Now, maybe you do want to do some thinking about it. Maybe if there's, enough stuff missing in there, you realize that your data file will be useless once you throw away all those missing values. You need to like put in an average or something like that. There are things you can do besides just drop everything, right? We're looking for null values now. There's none still. We're going to look at the, if we have to change the data type, we can say df.as type petal width cm. So we're going to take the petal width, and if it's not floating point, we'll make it floating point. We'll reassign that value because it actually creates a new object. So we'll take that object, we'll reassign it back to the data frame. So, this is the way we change something in place. The lazy way, another way to do it is to put an in place equals true argument on there. We're going to now look at the shape. It's the same darn thing. It's at 150, 6. Now we're going to do our visualizations, the bar charts, the scatter plots of different features. We're going to look at our strip plot. And of course, in this strip plot, we didn't say I think we're not doing an SNS.plot.show on here in this file. So yeah. Anyway, so I'm not going to run this code here. If we do the pair plot, and I just basically need to do SNS. Plot.show on here. There's our nice graph. And since I didn't do a show, I did a strip plot and then I did a violin plot. So plot.show says whatever you've built up to this point, it's going to display it. So down here, yeah, and is what we get. And of course, there's a plot.show lost here. If we were to do this is with the 4 features. You can see that many of them have lots of overlap. Others have minimal overlap. So your goal in this case is to just kind of look at the data and see where we have our best differentiations, right? What features help us with the best differentiation at each intersection of a thing with itself. Petal width versus petal width, right? We get the histogram for the 3 different species for that particular feature. So this is the petal width, what the distribution of that single feature is. And if I were to run this as so on and so forth, instead of this, I would get again, we add the new row and column with the IDs, and look, that's a perfect, yeah. And look at how great it is at differentiating between the species. We can now dump our histograms out. Actually, so what's happened, in case you're wondering, is this is a file that's been around for a while, and you didn't used to have to do the plot.show. And so now we have to remember to put that in there. So here's our grids. And again, here we add the KDE with a cut equals 3. What this is going to do is it's going to draw basically a smooth curve out to 3 standard deviations. You can say cut equals 2. It'll be shorter if here we do a cut equals 10. So you can see on this graph, the smooth curves go really far out from the data. Finally, we can do a use Plotly to do a 3D plot. This is kind of entertaining here. And basically, I have three of the features that I've chosen now: sepal length, width, and petal width. I can't do a four-dimensional 3D plot, obviously, because I can't see 4 dimensions. But as we start moving this around, zooming in and out, we can start seeing where the stuff feels like. As you play with this, you can see where the things are in the cloud. So you get a good idea of the visualization at that point. Now I look for correlations in the data. Correlation, and if I don't specify numeric only, it's going to try to correlate on categorical variables, which is not helpful. So we go ahead and do our correlations. And basically, everything correlates perfectly with itself, as you might expect. Where basically a correlation is saying on the X and the Y axis, the row and the column, how closely are these related to each other? And if the number is close to 1, it means they're very, very closely in sync. If the number is close to 0, it means they're kind of randomly distributed. If the number is close to -1, it means that they're varying in a negative fashion. Back to our slideshow briefly, significant correlations. Correlation is a number between 1 and -1. 1 is a direct correlation, strong positive. As X goes up, Y goes up. A correlation of 1 means they are moving in lockstep. Correlation of -1 means that as X goes up, Y goes down. Correlation of -1 means they're moving in perfect lockstep. A correlation of 0 is a weak correlation or no correlation. So that means that, if I try to draw a line here, I can draw a line in here, a regression line between these things, but my residuals are going to be really big. And if I start randomly changing points, this is a way to tell if you've got a good correlation. You try to randomly change one of the points. If your line doesn't move much, you've got a good correlation. If you change one of these points and your line starts wildly moving around, then you know that you've got poor correlation, right? So there's our DF correlation. We can do a heat map. And again, this heat map, I have not taken off the ID column. And what this is doing is it's showing me, again, the heat map has defaults on what it's going to do. We talk about how making a bar chart when you don't have 0 as the bottom of the bar chart is kind of misleading. It's lying with statistics. Right? In this case, the top of our bar chart is 1, and the bottom is not -1. So what we would like to see is, some value that's 0, where they're saying there's no correlation, is a specific color. But because the way things are laid out here on this thing here, we see that the moderate negative correlation is -0.4, -0.4. And minimal to no correlation, 0.11, right? That's a very weak correlation. There's only a 10% correlation there, are pretty indistinguishable. So don't get confused by this graph here. Again, strong correlation is close to 1 or -1, weak correlation close to 0. Positive correlation close to 1, negative correlation close to 0, or close to -1. We can also do bar charts. So if we do our bar charts as individual species, we'll see, of course, in here, the middle of the bar chart is the median. This is our 25th and 75th percentile. We take that interquartile range, we multiply it by 1.5 as the default. We build a fence at 1.5 IQR. So we take this, go down 1.5, around here someplace. We put a fence up, right? And then, of course, we measure the farthest observation from the median that is within the fence. Again, the example is, cows in a field, the cow that hasn't escaped. This cow got away. This flower escaped, right? It is an outlier. It is outside the field we want to see. So you can see as we look at our data that some of these have outliers. Some of them don't have any outliers. We can also do our bar chart with, the axis on the horizontal bar chart. You'll see horizontal bar charts on the exams because they're easier to fit onto the paper than a vertical one. Right. Now we can then remove outliers. We can take these charts that we've drawn here And we can say, again, this is illustration purposes. We are taking the percentile, ignoring the species, right? So here we're looking at sepal width. If we look at the sepal width up here, you can see there's no outliers here. There's no outliers here. There's a couple outliers in the Virginica. If we actually glomp those all together, what we end up is doing is throwing away Setosa observations and versicolor observations and keeping the Virginica ones. So this is kind of invalid. You have to look at the data close. This is an example of what's called Simpson's paradox. When you conglomerate things together, you get different results than when you take them apart. That's simplification of Simpson's paradox, but we'll get into it later. Anyhow, so what we can do is we can take our percentiles, we measure things, and we're going to basically just throw away anything that's outside that 1.5 IQR. So if the value is upper and lower, we just drop everything in the upper, and here we drop everything in the lower. And then we get a new shape with a smaller data set. So our new shape is 146. We threw away 4 observations. 30, 39. Yeah, we're going. Okay. So there's our correlation using the Pearson method. There's different ways of correlation. You have to read about that yourself if you want to. I'm going to go into that. There's our heat map. Again, Simpson's paradox. Yeah. Is a phenomenon in probability statistics in which a trend appears in several groups, but disappears or reverses when the groups are combined. So again, we saw that with outliers. You know, if we put them all together, we see outliers. If we take them apart, those outliers are no longer outliers. We do still see outliers, just only in a different species, right? Correlations between the data, if we have things that are strongly correlated, this can cause Simpson's paradox to appear, right? So they can be misleading when you've got confounding variables, you know, basically going together and confusing things, right? Correlation, causation, again, what we're measuring in correlation is how things vary together or not. We're not measuring does X cause Y, right? We're not saying anything about causation. A famous quote is correlation does not equal causation. Now, if you see strong correlation, you suspect causation, but you haven't proved it, right? So politicians are great about looking at 2 correlations and saying, well, this is causing this, because they're not mathematicians. So yeah, anyhow, but a correlation between variables does not automatically mean a change in one variable. There can be something else causing both to change, or there can be just a pure coincidence. Detecting and handling outliers, again, the box plots show where we are. Setosa has the smallest features, tightest distribution. Versicolor is kind of in the average on most of our features, except not on the sepal width. And Virginica has mostly the largest features, right? So we just can say that about our data, just kind of, you know, EDA is giving us intuitions, as it were, about the data. And we have to present them numerically, but we first of all need to get a feel for what we're really talking about here. Outlier mining. In this case, we're saying on the Virginica, we say that values above 4 and below 2 are considered outliers. And this is using the default outlier detector settings. You can define your outliers to be further away than 1.5 IQRs. You can say, I don't want to call something an outlier unless it's 3 interquartile ranges away, right? You can build your fence where you want to. The standard is 1.5 times the size of this box. So again, 1.5 times the size of the box, that's pretty close to the actual value. Down here, it's shorter in whisker because there's no values that are in this range inside the fence. Removing outliers, yeah, we did that in the code. You can go back and run that yourself. Main takeaways. Missing values can plague your data. Make sure you understand why there are missing values and and decide what you're going to do to deal with them, and write that down, right, as part of your analysis. You're running an experiment, you're doing a statistical analysis. One of the things you have to make sure is that you maintain your data provenance, where your data comes from, and you have to maintain the things that you did to the data, right? So if you did something that was invalid, you have to put that in your paper, at least in the appendix someplace, and someone will come back and say, you know, you did a mistake in your analysis here, and then you have to retract your paper, fix that and republish it. And you hear stories about that happening all the time, and it's part of the process. Provide a basic description of your features and categorize them. This will drastically change the visualizations you use and the statistical methods you will apply. You know, if your data has seasonal variations in it, then a simple linear regression is not going to work, right? Because seasonal variations follow sine curves, right? Understand your data by visualizing its distribution. You never know what you'll find. You know, get comfortable with how your data changes across samples and over time. Understand what time series looks like. Your features can have relationships. Make note of them. These relationships will come in handy down the road. Outliers can dampen your fun if you don't know about them. Understand where the outliers are. Don't necessarily throw them away, but know where they are, and mark down what your decision is about what to do with them. I mean, if you're looking at ages of employees at a company and you see an employee that's 450 years old, you can be pretty confident that is a data entry error. There's not actually a 450-year-old person walking into the office every day, right? Because it would be on the news if it were, right? But other outliers are just, that's the natural variation. And you collected a small enough sample that, you didn't catch that, and it looks more like an outlier than maybe it really is. Okay, so there we've dropped the petal width outlier. So here's an example of dropping outliers where we've simply said on a particular feature, right? Oh, yeah, you're not supposed to see that one. That's on your homework. Yeah. Okay. So again, outliers is technically part of EDA, but it's also part of data cleaning. If you find an obvious outlier, you want to clean it up. Okay. Next, I'm going to go ahead and stop and restart the recording because I'm not sure